Okay, let's begin the first laboratory in the Chem 113 or Organic Chemistry 2 sequence, which is the bromination of E-stilbene. In this case, rather than using straight elemental bromine, we'll be using a bromine equivalent of pyridinium bromide per bromide. This pyridinium bromide per bromide is a lacrimator, and as such will be handled carefully in the hood whenever possible. In this case, this reaction requires elevated temperatures for completion and requires a relatively large volume of solvent for the reaction. So we have set up our 50 milliliter round bottom flask with our stir bar intact, and we have our air condenser ready to go with the appropriate O-ring to ensure an adequate seal. Further, we have our heating mantle prepared, and we'll be setting up our heating setup before we begin to add our reagents to our flask. Okay, so to hook up our air condenser, make sure you have your O-ring to ensure an adequate seal. We simply just screw on the air condenser. We have our thermometer already placed inside our heating block, and we're going to nest our round bottom flask directly into the slot in our heating block. So now that we have our basic setup for this reaction prepared, we're now going to begin adding our reagents and weighing out the reagents that we need for this reaction. So as part of the process to weigh out our E-stilbene, we are going to prepare a weigh boat, and we are going to tare our balance. Make sure that both sides of the balance chamber are closed. Now that we have tared off the weight of our weigh boat, we're going to weigh out 600 milligrams of the E-stilbene reactant. Okay, so here is our E-stilbene. Remember, when you're dealing with communal containers, you always pour out a small amount into the provided dispensing petri dish. So we're going to pour out. And we can break up that chunk for the amount that we need to weigh. Okay, so we have our weigh boat, and we're going to transfer approximately 600 milligrams, making sure not to spill any. Okay, so let's now check and see how much we have dispensed. So we've only weighed out roughly 355 milligrams, so we're going to need about 245 more. So we're back at our weigh station, and we're going to need about 245 more milligrams of E-stilbene. So let's continue to dispense. It's always better to underweigh than overweigh rather than waste reagent. And you can always go back and add more if needed. So let's check how much we've weighed now. So we've overshot, so we'll need to remove a little bit. We'll come back once we've finally dispensed our 600 milligrams of E-stilbene in our weigh boat. Okay, so we've dispensed 602 milligrams of E-stilbene into our weigh boat. We're then going to transfer that into our 50 milliliter round bottom flask, and then we're going to weigh the weigh boat after the transfer to measure the amount of stilbene that still remains on our weigh boat. So let's go back to our station and let's transfer this stilbene. Okay, so we have our round bottom flask, we have our weigh boat, so let's begin to transfer the E still bean into our round bottom flask. So we'll resume once we've completely transferred all of the E still bean into our flask, and then we'll take our weight of our weigh boat. Okay, so we transferred, but we still have a little bit remaining on our weigh boat. So we're going to weigh the weigh boat that, remember, we still have tared on the balance, and determine how much still bean is left on the weigh boat. This ensures essentially that we have an accurate measure of how much material is inside our flask. So we're heading over to the balances now to begin to check the weight of the still bean remaining on our weigh boat. So this is the mass of E still bean still remaining on our weigh boat. So we've dispensed roughly 590 milligrams of E still bean reactant into our round bottom flask. Okay, for the solvent for this reaction, we have our 5 milliliters of glacial acetic acid that we are going to add to our round bottom flask. We're then going to prepare an additional aliquot of acetic acid, and we're going to utilize the acetic acid to dissolve the remaining solid in this round bottom flask. So we have an additional roughly 2 to 3 milliliters of glacial acetic acid that we're going to use to try to rinse the remaining solids into the bottom of our flask. We want all of our solids to dissolve, so we're going to carefully just add the remaining aliquot. Okay, so now we've gotten most of our solids dissolved and they're sitting at the bottom of our flask. Just give you a close-up view of that. So we have the majority of our solids sitting at the bottom of our flask. We're going to swirl a little bit to try to catch some of the remaining solids on the side. But as you notice, it is a heterogeneous suspension. However, at elevated temperatures, our E still bean will begin to dissolve in the glacial acetic acid. So for our first step, we are going to heat this sample on our heating mantle to approximately 130 degrees. And from that, once we have reached our target temperature for 5 minutes or our solid dissolves, we're then going to allow the sample to cool and begin to add the pyridinium bromide per bromide once the sample has cooled to about 40 degrees Celsius. Okay, so first things first, let's get the air condenser prepped and ready to go. You need that during the heating step. We're going to make sure the seal is properly secure. So you want to make sure there's a nice seal between your air condenser and the flask. And the sample may reflux a little bit. That's okay. That's why we have the air condenser, and that should help dissolve and catch some of the remaining solids that remain on the side of our flask. So we have it nestled. We have our thermometer ready to go. And what we're going to do is we're going to begin stirring our sample, and we're going to begin heating our sample to the target temperature of 130 degrees Celsius. And once our solid's dissolved, we'll have our pyridinium bromide perbromide prepped and ready to go, and then we'll be able to add the pyridinium bromide perbromide and then continue and actually begin our reaction. This is just a preparatory step to make sure our reactants are properly dissolved. So let's begin the heating, and you always have to set your target temperature on the heating mantle a little bit higher when you're first starting out. And we'll keep a close eye on our thermometer in the heating block and monitor the temperature throughout this dissolving process. Now, you may say that the stir bar that we currently have is a little large for right now. Don't worry, we're going to be adding more solvent in a little bit, and the stir bar will be more than needed from that dimension. Okay, so let's allow this sample to heat, and in the meantime, we're going to begin the process of weighing out our pyridinium bromide perbromide. In preparation for the cooling step, we have a water bath ready to go. As you've noticed, we're not anywhere close to the target temperature yet. So in the meantime, we are going to begin weighing out our pyridinium bromide perbromide. And for this purpose, we have a sealed container with a cap that we're going to use to minimize vapor exposure when we have to weigh the sample outside the hood. So we'll resume once we begin tearing our empty container, and then we begin weighing out the pyridinium bromide perbromide. So again, I have a holding beaker. I have my empty container with a cap, and I'm tearing this entire setup. And now I'm going to dispense the pyridinium bromide perbromide into my sealed container. I need about 1.2 grams of this material, so it's not particularly atom efficient compared to pure bromine, but nonetheless it has handling benefits. So we're going to begin to dispense the pyridinium bromide perbromide in the fume hood, as it is a lacrimator and it can cause irritation. And then we'll resume once we begin to dispense the sample. Let me just tear so that way we're at 0, 0. Okay, perfect. All sides of the balance chamber are closed, and this is the tared weight of our beaker and sealed container assembly. Okay, here's the pyridinium bromide perbromide. Again, we are in a fume hood to minimize the exposure to vapors generated from this compound or any dust generated from this compound. So we have our pre-teared empty container, and we're going to begin to add material until we have 1.2 grams in our container. Be really careful. You need to make sure you're wearing gloves with this compound, and you want to make sure to not spill any on your hands. So we'll check how much we've weighed, and then we'll resume and return to this station if we need to weigh more. I'm just going to cap it before I leave the fume hood, just to minimize vapor exposure, and we'll resume back at the weighing station. So currently we have about 1.07 grams, so we'll need a little bit more. So we'll return and we'll resume back at this weighing station once we've dispensed the 1.2 grams. Notice I'm weighing it with the cap on to minimize vapor exposure. If everyone in the class was weighing out this sample, you'd definitely begin to notice the fumes if it's not properly capped, sealed, and it's not dispensed in the fume hood. So we'll resume once we've dispensed our 1.2 grams of pyridinium bromide per bromide. So we've dispensed about 1.23 grams of pyridinium bromide per bromide, and we're going to get ready to transfer this sample in the hood once our E-stilbene and acetic acid has completed heating. So to give you a recap of what's going on with our E-stilbene and glacial acetic acid, we're trying to dissolve our E-stilbene and glacial acetic acid at elevated temperatures. We are heating to roughly 130 to 140 degrees Celsius for about 5 minutes or until our solid dissolves. Our sample is still heating, it's at roughly 80 degrees right now, so we're going to increase the temperature on our heating block and allow the sample to reach the target. We'll resume once we've reached our target temperature of 130 degrees Celsius. We have our water bath prepped and ready to go because we want our E-stilbene and glacial acetic acid to be hot, around 40 to 50 degrees Celsius, but not too hot to the point where we begin to get a reaction when we add our pyridinium bromide per bromide. We'll initiate the reaction at elevated temperatures once both our reagents have been mixed. This is a pretty fast reaction. We just have to get all of our reactants set up and ready to go and dissolved in our solvent. So as you have noticed, our sample is now approaching the target temperature and almost all of our solids have dissolved. We're not quite there yet, so we're going to let it heat for a few more minutes. And once all of our solid dissolves, then we'll begin the next cooling and transfer process. So our sample has finished heating at the target temperature for at least 5 minutes. So now what we're now going to do is we're going to begin to allow our sample to cool. So we're going to take it off of the heating mantle plate, and we're going to allow our sample to cool to around 40 to 50 degrees Celsius or until it's slightly warm to the touch. And then we're going to transfer the pyridinium bromide per bromide in the fume hood into the flask. So allow us to take this off of the heating mantle. We're going to keep the heating mantle hot because we're going to use it again when we want it to maintain at the target temperature. But we're going to allow our sample to cool, and once our sample is cooled and is ready for the heat transfer, ready for the transfer of pyridinium bromide per bromide, then we'll resume this recording. So we'll let our sample stir and cool, and once it is cooled for a few minutes, we'll be able to place it in our water bath to accelerate the cooling process. We don't want to put it in immediately and trigger heat shock. So we'll resume once our sample has cooled a little bit, and we're ready to begin the transfer of pyridinium bromide per bromide. Okay, so we have our reaction flask that is warm and contains all of our dissolved E stilbene. We have our pyridinium bromide perbromide, and we have some glacial acetic acid prepared for the rinsing step. We're now going to transfer our pyridinium bromide perbromide into our reaction flask, rinse with some glacial acetic acid, and then we'll be prepared for the heating step. So we'll resume once we've completed this transfer of the pyridinium bromide perbromide. Okay, so we finished transferring the pyridinium bromide perbromide. Of course, we weighed out a little bit of extra pyridinium bromide perbromide to account for losses during transfer, and this reagent is used in excess regardless. What we're going to do now is we're going to rinse with a 6 milliliters of glacial acetic acid. We're going to rinse any pyridinium bromide perbromide remaining on the side into our reaction vessel. We want it to be mixed with our reactant E stilbene, and in fact we're already starting to see some reaction and precipitation of the product dibromide. The product dibromide is not particularly soluble in this solvent system. So once we've finished adding our glacial acetic acid and rinsing down the pyridinium bromide perbromide, we can reinstall our condenser head and then move our sample to heating. So we'll resume once we have our sample back on the heating mantle. Okay, so we have our sample back on the heating mantle, and now what we're going to do is we're going to heat the sample to 130 degrees Celsius for approximately 5 minutes. So we're going to place our sample down on the heating mantle, and once we've reached the target temperature, we will begin timing for 5 minutes. As you notice now, with a greater volume of solvent, we're going to need a little bit stronger stirring to allow our reactants to mix. Once we reach the target temperature, we may still not have a homogeneous solution, as the product mesostilbene dibromide is insoluble in glacial acetic acid, even at elevated temperatures. So one sign that the reaction is going to completion is the generation of a precipitate even at elevated temperatures. So we're going to allow our sample to reach the target temperature of 130 and then heat for approximately 5 minutes until the reaction has gone to completion. So we'll allow this sample to sit and we'll let the reaction proceed for 5 minutes. So we're still allowing our sample to heat. It has finally reached the target temperature of 130 on our thermometer. So we'll allow our sample to heat for 5 to 6 minutes, and then we'll begin isolating the product. In the meantime, we're going to prep a water bath, and we are going to prep, and we've already prepped our filtration setup. So we'll continue to allow this sample to heat. So as you have noticed, the reaction mixture has begun to change color from the typical dark red color of the pyridinium bromide perbromide to more of a light yellow or orange color. As you've also noticed, there's the presence of a precipitate even at elevated temperatures. So we'll allow this reaction to continue to proceed, and we will isolate the product in approximately 3 minutes once the reaction has gone to completion. We have the water bath prepped and ready to go, and we have also prepared our aliquots of water that we are going to use to precipitate out our product. So we have our graduated cylinder containing deionized water ready to go. So we'll wait a few more minutes for this reaction to go to completion. Then we'll allow the reaction mixture to cool and begin isolating the product. Okay, as we have allowed this reaction ample time to proceed and we've completed the required 6-minute heating period, we are going to now turn off the heat, and we're going to take our sample off of the heating mantle. We're not going to put it directly onto or into our water bath. That's a recipe for heat shock. but we're going to take our sample off and then allow the reaction mixture to cool with stirring. So we'll continue to allow this sample to cool, and we'll resume once it has reached about 40 to 50 degrees Celsius where it's slightly warm to the touch, and then we'll begin to add the water and then place our sample in the water bath and ice bath. Okay, so our sample has finished cooling, and I've taken the liberty of placing it into a water bath. Now what we're going to do is we're going to remove the air condenser, and what we're going to do is we're going to add 12 milliliters of deionized water. Now you really want to make sure your flask is secure, because the last thing you want to do is to have to isolate it from this giant 250 milliliters of water. Okay, so we're going to add 2 portions totaling 12 milliliters of deionized water to our flask, and this will help facilitate the precipitation process. Because of course our product is not particularly soluble in water, and as you notice, upon addition of the first aliquot of water, we begin to see massive amounts of solid generated, and we notice a quite noticeable change in color for our reaction mixture. So now let's add our last 2 milliliters of deionized water to reach our total of 12. Okay, and as we've noticed, we're already starting to see the precipitation of solid. To further facilitate this process, as our sample is cooling and is now approaching room temperature, we are going to immerse it in an ice bath for approximately 5 to 6 minutes to further facilitate the precipitation of our product. So we'll resume once I have the ice bath prepared. So we've prepared our ice bath, and now we've immersed our sample into the ice bath, and we'll let it sit in the ice bath for 5 to 6 minutes to allow the remaining amount of solid to precipitate. In the meantime, as you've noticed off to the side, we have our filtration setup almost prepared. We have our Hirsch funnel with our piece of filter paper, we have our filter flask, we have our collecting flask, and we have our vacuum line all set up and ready to go. We will begin the filtration process in about 5 to 6 minutes once all of our product has precipitated. So we'll resume in about 5 to 6 minutes once all of our product has precipitated. Okay, so we have allowed our product to precipitate. As we can very clearly see, we have a fairly large amount of solid that is precipitated out of this reaction mixture. Notice at the bottom we have this giant lump of solid. That's what we're going to be collecting via filtration. We have our Hirsch funnel all set up and ready to go. And as a preparatory measure, we're not going to throw away the ice bath just yet. We're going to keep this mixture cold. We're going to use this ice bath to chill our water. So we're going to use that to help cool the water aliquots that we're going to use and we're going to utilize in the rinsing steps. So we have our Hirsch funnel set up. We have our filter paper in the funnel and we have our trap set up and ready to go. This entire setup is under vacuum. And now what we're going to do is we're going to begin to carefully filter our reaction mixture. And we're going to want to use a stirring rod to help facilitate this process. Okay, so we're going to very carefully transfer as much material as possible into the Hirsch funnel. Okay, perfect. We're all set, so let's begin this careful transfer. We're trying to get out most of the liquid at first, so then we can start to begin to really start filtering a lot of the solid. Again, we're using the stirring rod to help facilitate the transfer. And don't worry, once we've drained most of the liquid, we can begin to really start to tip the flask over and begin to filter most of the solid off. But for now, we just got to make sure that we're not overloading our funnel. A nice slow and steady rate. Okay, that's our first pass. We're just going to wait a little bit for the remaining liquid to drain, and then we'll continue the transfer process. Okay, more of the liquid has drained, so we can continue the transfer process. We're going to agitate the mixture to help pull more of the solid. Now we can start to go direct. Let me set this off to the side like so. So we'll continue to filter, we're continuing to collect solid, and we'll continue this filtration process until all of the solid has been effectively collected, and then we'll be able to rinse the solid. It gets a little bit slow once you collect a fair amount of solid, as the filter begins to have to pull while there's solid stuck in the filter. So we'll continue this process of filtration as the solid is collected and as the subpertinent filtrate liquid is drained. Now don't worry about some of this solid that's still trapped. We're going to get it with some rinses, and that'll help us improve our collected yield. Though, especially for this experiment, the main importance is getting pure product and relatively pure product, so that we can either utilize it for future steps and get reasonable analytical data. So we're starting to collect the majority of the solid. We're going to have to be a little bit careful, as before we do the rinses, we may have to move our filtrate to a separate flask, but that's okay. Nothing that can't be managed. Don't worry, we're going to remove that. We're going to remove the stir bar that dropped in, and we'll resume once we begin the rinsing steps. Because we still have some material left, we're going to rinse it into our collection flask, so that way we can collect all of our solid. Okay, so we're ready to begin the rinsing steps. So what we're going to do is we're going to utilize three 2 ml portions of chilled water. And what we're going to do is we're going to really try to collect as much of the solid as possible. And the rinsing steps also serve to purify the solid that we have filtered. So we'll continue these rinsing steps, first with the 3 milliliter portions of water. Let me correct myself. The 2 milliliter aliquots of water 3 times. Again, we want to try to get as much of the solid that's remaining in our flask as possible, while also using these rinses to purify our solid. So as this is getting a little bit full, we're going to pour out our filtrate, and we'll resume once we've completed that draining process. Since you never want your collection flask to get too full. So we'll resume once I've drained the collection flask. Okay, so we've drained our filtrate into a collection flask, and I really want you to be able to see collected already on our filter paper is a ton of this beautiful solid for our meso-stilbene dibromide. We still have some rinsing steps to continue on with, so we'll continue our rinsing process with our last aliquot of chilled deionized water. And again, we want to make sure that we try to catch as much of the solid that we've collected in our flask and transfer it into our filter funnel. These rinses are also serving to remove trace impurities from our sample. Now, you may ask, why do we follow up with a rinse with acetone? Well, acetone is a wonderful drying agent. It is quite useful for drying samples and is useful to remove trace amounts of water from our sample. So, what we're going to do is we are going to rinse with a small volume of acetone, and we're going to use those rinses to help dry the solid that we've collected on our filter funnel. It also serves to help remove any trace impurities. So we're going to rinse with 2 milliliter aliquots of acetone to dry our sample. Okay, so here is our 4 milliliters of acetone, and we're going to rinse our flask and our collected solid precipitate with the acetone. This is going to help dry our sample and remove any trace acetone-soluble impurities. I find the more small volume rinses you do, the better. That's why I'm doing rinses with 1 milliliter aliquots instead of 2, just so that way we have more chances to collect any remaining solid. Okay. So our flask is relatively clean. We've almost gotten out most of the solid. And we're going to complete with the last 2 rinses with acetone. Okay, so now we have our solid collected, and now what we're going to do is we're going to allow our sample to air dry for about 5 to 10 minutes, and once our sample is dry, we'll then transfer it to a piece of weigh paper and determine our final collected yield. So in preparation for our final weighing of the dry meso-stilbene dibromide product, I have prepared a piece of filter paper and teared it so we can record the initial weight of the filter paper before solid is added. One thing I would like to highlight as we wait for our sample to dry is the pretty clear difference between the filtrate, which is primarily consisting of impurities and byproducts from the reaction, and our pure solid precipitate, which is a nice white crystalline solid. So another thing that's pretty interesting to consider is that you can notice a pretty substantial change between the initial mass of reactant and the isolated mass of product, which is expected in dibromination, considering that we are increasing the molar mass of our product compared to our reactant. So we'll continue to allow this sample to air dry, and after about another 3 to 4 minutes, we'll transfer the sample to our prepared and pre-weighed piece of weighing paper. Okay, our sample has finished drying, so we're going to turn off the vacuum. Okay, so now we have collected in our Hirsch funnel this beautiful crystalline solid, and we're now going to transfer it to our pre-weighed tared piece of weighing paper. Isn't that just great, collecting a large amount of pure crystalline solid? Well, we don't know if it's pure just quite yet, but we will figure that out soon enough because we have plenty of material to measure the melting point under evacuated conditions. We can definitely take an IR spectra of this compound, and we can even take an NMR spectra. So we'll resume once we've completed transferring all of this solid and we're ready to weigh the solid on our balance. Okay, so we finished transferring all of our solid from the filter paper and Hirsch funnel into our piece of weigh paper, and now we're going to bring this over to the balance. So here is the final mass of our isolated stilbene dibromide product. So as you notice, our isolated mass is substantially greater than our starting mass as we gained 2 bromines, and the molar mass of our product is much greater than that of our reactant. So from this, you'll be able to calculate the percent yield data for this reaction. We're now going to collect some physical property data as well as IR and NMR spectra for this isolated solid to determine the purity, because a high yield of impure material is not a true high yield. We need the purity to inform our yield calculations. So we'll start with melting point and then continue on with the other spectral analysis. Okay, so as part of our efforts to collect physical property data, we're going to need to collect an evacuated melting point. As a result, because we need to collect an evacuated melting point, we are going to need to generate an evacuated melting point tube. So we're going to seal off the ends of multiple pipettes, then we're going to load it with a small amount of solid, and then from there, we're going to seal off the tubes under vacuum. So we're going to start off with our first step, which is simply sealing off the ends of each of our Okay, so we have the micro burner set up and ready to go. So now we're going to seal off the ends of each of our pipettes in preparation to generate an evacuated melting point tube. So to do that, we're going to gently immerse the tip of the tube into the flame. We're going to carefully swirl it, and if we've done everything properly, we should end up with a nice bulb at the end. So as you notice, it's hard to get a good zoom in, but we'll show a close-up of this later. And we're going to allow each of our pipette tips to cool. It's important to rotate your pipette so that way the seal ends up making this nice bulb. You want it to be completely sealed, otherwise when you turn the vacuum on, your solid's just going to disappear out of the tube. We're going to make a few of these just so that way we can do multiple replicate runs, and so that way we aren't too worried about So we're going to wait for these pipettes to cool, and then we'll resume with generating our evacuated melting point tube. Okay, so we have our tubes loaded with solid. We've applied vacuum and we haven't noticed our solid pulled up the vacuum line, so we've done a good job ensuring that this bottom bulb seal was appropriate. Now what we are going to do is we are going to very carefully heat this juncture, keeping in mind that we are not to directly heat our solid. We're going to heat this juncture. Okay, perfect. As you notice, the glass is now malleable. And now what we're going to do is under vacuum, we're going to heat until it's malleable. And then we are going to tie off the end. Okay, it's almost there. Okay, perfect. So as you notice now, we are left with a tube that is sealed at the other end. And we're going to make a second seal. Just so that way we are positive that it is completely sealed under vacuum. We're going to make a few more of these as we allow them to cool. We're going to hook up our second tube to the vacuum line. Notice the solid hasn't jumped up. That's a sign that our vacuum seal is good. Okay, we've created a seal. And then just like before, we're going to create a second seal just to ensure not the best, but we have created two seals and we've ensured that this is stored under vacuum. Let's keep going with this, and we'll conclude once we have at least 3 tubes prepped. Let's create a few more, just so that way we have some backups if we need to go back. Okay, and then one last one. Okay, so we finished creating our evacuated melting point tubes. We'll allow them to cool and we'll resume at the melt temps, where we will measure the evacuated melting point of our mesostilbene dibromide product. Okay, so we have our mel temp set up. We are already beginning the heating process. We have our sample loaded into our mel temp. This is an evacuated tube. The melting point will be somewhere around 200 degrees Celsius, so we're going to have to spend a fair bit of time on that. And you'll see posted on Canvas a time lapse of this process. If you zoom in, you can see the image of our solid sample in the melting tube. We'll get some higher resolution images using another camera. In the meantime, we've noticed that we're already at 80 degrees Celsius. Again, we are looking for the first moment that a liquid drop is observed, all the way until all of the solid has completely melted and we only observe liquid. That is going to be our melting point range for this sample. So with that in mind, we'll resume once our sample begins to melt and when we record our first temperature. So we are already at around 180 degrees and we do not see any apparent melting occurring. So we'll accompany this recording with some phone pictures and some other pictures using our other cameras to help you observe the melting process, and you'll see some recordings of this melting process. So we'll resume once we're taking our initial temperature reading. So we have completed the mel temp measurement of the melting point, and we saw both the sample when the first drops of liquid appear to once the sample has finished melting. and we were able to record the temperature range. You'll see the data for the follow-up runs posted on Canvas. Okay, so now we are going to take an NMR spectra. So we have our NMR tube. We're going to load it with approximately about 2 to 3 milligrams of sample, and then we will dissolve our sample in approximately 1 milliliter to 0.5 milliliters of deuterated chloroform. You can't use non-deuterated solvents to take an NMR spectra easily, as the solvent peak will swamp out your compound peak. So let's resume once I've loaded our sample into the NMR tube. So I've loaded our sample into the NMR tube, and I'm now going to dissolve it in deuterated chloroform. So we finished dissolving our sample in the deuterated chloroform. So now we're going to take it over to our benchtop NMR and take an NMR spectra of this compound. So as part of preparation of the KBR pellet, we are performing solid dilution. We've taken an equal volume of our sample and potassium bromide, which we've already dispensed, and we've mixed it in a 1-to-1 ratio. This is the product after the second solid dilution step. We're going to repeat this process by taking another equal amount of KBR and mixing it with our KBR and product sample. So in this process, we are ensuring that our KBR pellet will form a nice clean disc, as well as ensuring that we see a reasonable product signal via IR. So again, this entire mixture will go into the following KBR disc press, and we need 10 milligrams of this mixture. This is our third solid dilution, so we're going to need to do one more solid dilution, and then we're finished. I want to make sure that the solids are thoroughly mixed. Now we're going to dispense our last amount of KBR for our solid dilution, using a different spatula, of course. Okay, so now we're going to mix. Okay, so now that we've finished the mixing process, we're going to load our sample into this pre-tared KBR pellet press. So we've loaded our KBR pellet with 10 milligrams of KBR and product mixture, and now we're going to load it into our KBR press to generate our disc. So we have our KBR pellet press ready to go. We're going to load it into the pellet pressing device to generate our KBR disc. Okay, so after pressing, here is our complete KBR disc. You really don't need a ton of material, and now we're going to load this into the IR. So we've loaded our KBR disc into the IR. We're now going to close the chamber. And we're going to begin collection by setting the scan option, right? Okay, perfect. So we're beginning to collect the IR spectra for our sample, and the IR spectral, as well as the NMR spectra collected in earlier trials, will be posted on Canvas. So we're going to begin the Bilstein test. So we have our copper wire set up. We're going to collect a small amount of our sample on the copper wire, and we're going to place it about 1 to 2 centimeters above our flame, and we're going to observe the color. So we'll do a few more runs of this just so that way it's visible. So now we're going to do another run of the Bilstein test, which confirms the presence of a halogen via combustion on a copper wire. So we have our copper wire. Okay, so we have our sample. And I'd like you to observe the flame characteristics and color. So that was the Bilstein test for the presence of a halogen. We're now going to resume with a combustion analysis test. Okay, we're now going to do combustion analysis. We have a small amount of sample, and we're going to observe how the sample combusts to look for the presence of different functional groups, primarily an aromatic, which is indicated by a dark, sooty flame. Record your observations and note any functional groups present as the result of these two combustion analysis tests. Okay, we're now going to do a test using nitric acid and silver nitrate to detect the presence of a halogen. First and foremost, we're going to dissolve our sample in a small volume of nitric acid. So now that we've dissolved our sample in nitric acid, we're going to add a small volume of silver nitrate. And we should see, if we have a halogen, the characteristic color, the characteristic white precipitate. We should see this characteristic white precipitate associated with a silver halide. Okay, so as part of the test for an alkyl halide, we're going to take our sample and treat it with an ethanolic silver nitrate solution. So as we can see, we have a suspect precipitate that was generated in this process. So to verify that this precipitate is in fact an alkyl halide, we're going to treat this mixture with a small amount of nitric acid. Now we're going to agitate our mixture, and if our solid persists, then that is strong evidence to suggest that we happen to have an alkyl halide present in our mixture. So as we observe, our precipitate has continued to persist, and that provides strong evidence that we have an alkyl halide present in our product. Next, we're going to do the Belston test for ignition. We should see a characteristic sooty flame and a green flame. The green flame is unique if we have an alkyl halide and we heat our sample on a copper wire. So let's see what we observe. So we have our sample, and I'd like you really to focus in on the color and characteristics of the flame as we heat our sample. Let's do another trial of this. As we can see, we see a characteristic green flame, which is positive confirmation of a halogen. So we have now completed Lab 2B. We have synthesized our desired dibrominated product. We've characterized it using a range of spectroscopic methods and measured the physical properties and chemical test properties of this compound. From the data provided through this video and Canvas, you can complete your laboratory report.